Good morning dear students, this is Bonani Prakash. I welcome you all to today's video. Here we are doing the chapter Matrices. So here we were doing the exercise 3.3 and two questions are left. So question number 11 is, if in question number 11 it is given that if A, B are symmetric matrices of same order, then AB minus BA is a skew symmetric matrix, zero matrix, identity matrix. Which one of these four is true for AB minus BA? So for that, suppose we are writing, since A is a symmetric matrix, so A transpose is equal to A and B transpose is equal to B, since both are symmetric matrices. Now we will find the inverse. Now we will find the transpose of AB minus BA. So AB minus BA whole transpose. Since we know A plus B whole transpose is equal to A transpose plus B transpose, so A minus B whole transpose is also equal to A transpose minus B transpose. So here we can write AB whole transpose is minus BA whole transpose. Now from here we can write B transpose A transpose, and here we can write A transpose B transpose. Now since A and B both are symmetric matrices, we can replace this B transpose by A and we can replace this A transpose by A. Now from here we can take minus 1 common, so it will become AB minus BA. So AB minus BA whole transpose is equal to minus AB minus BA. So AB minus BA is a skew symmetric matrix. So the answer will be option A. Let us move to the next question, question number 12. In question number 12 it is given, if matrix A is given, then A plus A transpose is equal to I if the value of alpha is. Now see here, A transpose and A both are of order 2 by 2. Then the identity matrix will also be of order 2 by 2. Let us write. So A transpose will be equal to cos alpha sin alpha minus sin alpha cos alpha. Now if we add A plus A transpose, we have to add the corresponding elements. If we add these two, we will get 2 cos alpha. Now we will add minus sin alpha, so it will be 0. Now we will add sin alpha minus sin alpha, again 0, cos alpha plus cos alpha, 2 cos alpha. And it is equal to the identity matrix I. So we can write it as 1 0 0 1. Now if two matrices are equal, then their corresponding elements are also equal. So from here we can write 2 cos alpha is equal to 1. So cos alpha is equal to half. So whenever cos alpha is equal to half, what can be the value of alpha? Value of alpha will be 60 degree. 60 degree means pi by 3. So the answer will be option B. So with this our exercise 3.3 is completed. Now move to elementary operation or transformation of a matrix. So there are 6 operations or transformations on a matrix. 3 of which are due to rows and 3 due to columns, which are known as elementary operations or transformations. So, there are 6 transformation we can do in a matrix. 3 are for rows and 3 are for columns. So, first one is the interchange of any 2 rows or 2 columns. Symbolically, the interchange of ith row and jth row denoted by this Ri, Rj, and interchange of ith and jth column is denoted by Ci, Cj. That means whenever we are doing the transformation taking the rows, we will represent it by capital R, and whenever we are doing the calculation taking the columns, then we will write C. Here one example is given. Let us see the example. A matrix A is given, and after that they have written we get another matrix. Applying R1 and R2, that means R1 and R2 are interchanged. This means in place of R1 they have written R2, and in place of R2 they have written R1. So, in this way interchange of any 2 rows can be done. And the next transformation is the multiplication of the elements of any row or column by a non-zero number. That means we can change a row or column by multiplying it by a non-zero number. See here the example is given for column. Now matrix B is given. Now see, you compare these 2 matrices. So here you look at the third column. Here you will see the third column is multiplied by 1 by 7. And here it is written column 3 is transformed to 1 by 7 into column 3. That means they have multiplied the column 3 by 1 by 7. So, in this way also we can multiply any row or column by a non-zero number. Here non-zero number is 1 by 7. Now, this example is given for column. You can multiply any one row by a non-zero number. So, this is the transformation number 2. Point number 3 is the addition to the elements of any row or column, the corresponding elements of any other row or column multiplied by any non-zero number. That means here we can add the elements of any row or column, the corresponding elements of any other row or column multiplied by any non-zero number. So, from there it will be hard to understand. Let us see one example given here. So, see the example. Here it is given the matrix C. Now, see what transformation they have done here. R2 is, this R2 is transformed to R2 minus 2R1. Now, see, you compare this R2 and this R2. The R2 is 2 and minus 1. Now, to get 0, how they have got this 0? So, they have done what? 2, taking this 2 minus 2 into 1. Now, from where this 1 is coming and from where this 2 is coming? Now, see, they have written R2 is transformed to R2 minus 2R1. That means 2 minus 2 into 1, so that they will get 0 here. So, from here we are getting 0. Now, for the next element, that is in the first matrix it is minus 1 and in the next matrix it is given minus 5. How they have got this one? So, the transformation was R2 minus 2R1. So, minus 1 minus 2 into 2. So, minus 1 minus 2 into 2. So it will be minus 1 minus 4, so minus 5. In this way also we can transform the matrix. Now this transformation they have done taking the rows, we can do it taking the columns also. Now here they have done the subtraction, we can do the addition also. So these are 6 elementary transformation of matrices, 3 are for rows and 3 are for columns. Let us move to invertible matrices. What is invertible matrix? So definition 6 is given. If A is a square matrix, A should be a square matrix of order m, and if there exists another square matrix B of same order m such that AB is equal to BA is equal to I means identity matrix, then B is called inverse of matrix A and it is denoted by A inverse. So from here we can understand that two matrices, and both the matrices should be square matrix and both the matrices should be of same order. If we can write AB is equal to BA is equal to I, then from here we can say B is the inverse of A, and we can denote this B by A inverse. In the same way, we can also say if AB is equal to BA is equal to I, then A is the inverse of B. A is the inverse of B. So from here we got to know that if AB is equal to BA is equal to I, then B is called the inverse matrix of A and it is denoted by A inverse. We can also say that A is the inverse of B. So if AB is equal to BA is equal to I, then A is the inverse of B and B is the inverse of A. Now here one example is given. See, the two matrices are given A and B and they have done A into B. So from there they have AB is equal to I. I means the identity matrix. Now you see from here A is a square matrix of order 2 by 2. B is a square matrix of order 2 by 2. The identity matrix they got from here multiplying these two matrices, that is also of order 2 by 2. Now from BA also they have their identity matrix I. So from here AB is equal to BA is equal to I can be said. So B is the inverse of A and A is the inverse of B. So in words they have written B equal to A inverse. That means B is the inverse of A and A is the inverse of B. So A equal to B inverse. So note is given. So first one is a rectangular matrix does not possesses inverse matrix since for products BA and AB to be defined and to be equal, it is necessary that matrices A and B should be square matrices of same order. That means if A and B are not square matrices of same order, then they cannot possess the inverse matrix. Point number B is if B is the inverse of A, then A is also the inverse of B. That means if AB equal to BA is equal to I, then A is the inverse of B, B is the inverse of A. So come to theorem 3, and theorem 3 is given uniqueness of inverse. That means if inverse of a matrix exists, then the inverse will be unique. Inverse of a square matrix, if it exists, is unique. That means if matrix A is given and the inverse of matrix A exists, suppose the inverse of A is A inverse, then it is unique. This A inverse is unique, and there cannot be any other inverse of A other than A inverse. So, the inverse of a matrix is unique. So, this is the uniqueness of inverse. Next theorem is theorem 4, and the theorem 4 is if A and B are invertible matrices. Invertible means inverse of A exists and inverse of B exists. If A and B are invertible matrices of same order, then AB whole inverse is equal to B inverse into A inverse. In the proof it is written, from the definition of inverse of a matrix, we have AB into AB inverse is equal to I. This will be I. So, we know if two matrices are invertible, then we can write AB into BA is equal to I, where B is the inverse of A or A is the inverse of B. Now, if we are talking about the matrix AB, then the inverse of matrix AB will be AB whole inverse. So, we can write AB into AB whole inverse is equal to I. Now, in the next line they have multiplied both the sides by A inverse and they have done pre-multiplication. Pre-multiplication means they will write A inverse first. So, from here A inverse into A, B, AB whole inverse, and if we multiply A inverse by I, we will again get A inverse. From A inverse into A, we will get this I. Next, I into B is B. In this line again they have done the pre-multiplication by B inverse. Now see, here also they have written B inverse first in both the sides. Now from B inverse into B we will get I, and if we multiply this I by this AB whole inverse, we will get AB whole inverse. So, from here we get AB whole inverse is equal to B inverse into A inverse. So, it is proved. In theorem 4 it was given, if A and B are invertible matrices of same order, then AB whole inverse is equal to B inverse into A inverse. So, it is proved.